Thanks. I'm Liam. Thanks for coming to my talk. Yeah, I'm going to talk about log derivative lookups, including CQ and ProtoStar lookup, maybe, depending on how quickly it goes. Yeah, so just some motivation, I guess. Probably all heard of lookup arguments. Like, what are they? Why do we care about them? So snarks allow us to prove that we know some witness that satisfies a relation. So you may have heard of like R1CS. When the relation is convenient to arithmetize, meaning that you can express it with additions and multiplications in a field, that's great. But often that's not the case. Not all relations that we care about arithmetize well. For example, range checks, right? Suppose we want to show something is in a range. One way to do it might be to decompose it into bits, which is something people did. But another way would be to use a lookup argument. So a lookup argument allows us to show that some values belong to a table. And the table can be totally unstructured, although some lookup arguments are for structured tables, but just in general, it can be unstructured. It can contain any values. So this is good for messy operations, for range checks, for binary operations, for things that don't arithmetize well. In fact, normal computation often does not arithmetize well, things you would do on a computer instead of inside of a circuit. Yeah, so why should you care? There's lots of like really cool work in lookup tables, and they're a big part of modern snarks and making things fast. They can be or the lookup argument itself can be independent of table size, so I'll talk about that with CQ, which is sort of part of the calc line of work. And so effectively you just pre-compute all of the lookups and then look them up as needed, so you don't do cryptographic work dependent on the table size when you're proving. And I guess the kind of end game for all of this, as you may have heard, is the lookup singularity. Lookups are sort of universal primitive. You could do everything in theory with really fast lookups, so worth investigating. So that's lookups at a high level. What is a log derivative lookup? Log derivative is a kind of intimidating term. We'll consider a simpler case than a lookup argument, which is just a multi-set equality. So suppose A and B are multi-sets of field elements. We want to show that they're the same. If you think of them as sort of sequences, right, a multi-set forgets the sequential structure. So if we could somehow forget the sequential structure, then we might arrive at some object that is the same if and only if the multi-sets themselves are the same. And so this is sort of common product identity. I'm not actually sure where it originally was introduced, but forgive the math. It's not pretty like LaTeX, but so you can see, like, if you take the product over the elements of A and the product over the elements of B, the two polynomials will be the same if and only if the multisets are the same, even if they're in a different order. So you can check that they're equal as multisets rather than sequences. So one thing we might want to do is use addition instead of multiplication. Is this possible? It is. We can take this product and just sort of do this kind of strange transformation and turn... Am I standing in front of the slides? Turn it into sums, right? So instead of multiplying over x minus a, we would sum over 1 over x minus a and sum over 1 over x minus b. So it should be pretty easy to see from completeness that this will hold if the multisets are the same. But maybe it's not obvious that it will never hold if they're not the same, which is what we would want for a lookup argument. So this transformation is actually sort of formalizable, and this is where the log derivative term kind of comes from. So the logarithm from calculus, say, takes numbers to numbers and multiplication to addition. It turns out that there's actually a purely algebraic version of the logarithm called the log derivative. If you take the derivative of a logarithm, it's actually just the derivative of f divided by f, where here the derivative can be defined formally. And because this operation is entirely algebraic, it's well defined over finite fields. unlike, a normal logarithm. Yeah, so you can kind of see if you have your factor x plus a, and you apply the log derivative to it, you take the derivative of it and divide it by x plus a, and that simplifies to 1 over x plus a, which is exactly what we had here. And the products go to sums. So one really nice aspect of this transformation is that it pulls the exponent in the product version into the numerator of the log derivative version, right? If we take the log derivative of this x plus a to the m, it just becomes m divided by x plus a. So yeah, and then how do we actually build the lookup? We have our values we want to look up, xi, our table, b, these are just multisets, and we'll encode the multiplicities, that is the number of times each x occurs in the table in m, and then we check this equation. And so each sort of 1 over x minus an element of a should correspond to like 1 of the 1 over x minus t. That's what the lookup is checking, right? It's checking that each x is in B. And so heuristically, right, like if there were an x on the left-hand side that were not in B, it wouldn't be possible to cancel it on the right-hand side by manipulating m. Yeah. And there is this important caveat that the m's have to be smaller than the characteristic of the field. This doesn't come up so much with elliptic curves because the characteristic is very large. But if you were working in, say, small field Fry, a 31-bit field, it's not inconceivable that you would actually achieve a multiplicity that high. Or certainly if you were in like a binary field or something. So it's important to keep that in mind, but it's not, like I said, really relevant for elliptic curves. So maybe work through a simple example. We have our table of integers from 0 to 3. We have our values that we want to look up in the table. So we can count the number of times 0 occurs in A, which is 1, the number of times 1 occurs in A, which is 0, and 2, which is 2, and 3, which is 1. And if we plug in these sort of values into our equation to check, we find that they balance. The blue terms sort of map to the same thing on the right-hand side. So it works. But if we had some value in A that was not in the table, say 7, then there would be this extraneous term on the left-hand side, right? Because there's a new value in A, and it doesn't really line up with anything on the right-hand side. So I wrote m's on the right-hand side. It turns out you cannot find a vector of m's that satisfies this equation. So this is kind of why it's sufficient for you to just know m. You don't have to prove anything about it besides that it satisfies the lookup equation. So we can turn this into a kind of simple interactive protocol where the prover is going to send their values to be looked up, the table, which you could imagine is just agreed on in advance, the multiplicities. The verifier chooses some randomness, which is what we will use to evaluate this expression. So this is a rational function, and we're going to check it at a random point in order to check that it holds everywhere. So we pick a beta, and then the prover will compute these reciprocal terms that show up in the sum and send commitments to those. And then the verifier just has to do a simple sort of sum check and zero check consistency on the sent A's. So this is all pretty simple. I mean, this kind of allows us to, in some sense, arithmetize lookups, right? We're taking this messy operation and converting it into something that's easier to prove in Snark. So there's a bunch of different protocols that build on top of log derivative lookups. Among them, MV lookup, which sort of independently rediscovered log derivative lookups. has some interesting optimizations regarding combining terms. So these zero checks with the AI, you could imagine that we could add up different reciprocals and they might increase in degree. So that's one thing MV-lookup does. CQ, which is, I guess, the most recent or, almost most recent work in the calc line of big table lookups, uses log derivative lookup to check, perform lookups independent of table size. ProtoStar, which you heard about in the last talk, also uses a variant of log derivative lookups and is also independent of table size during folding, which is really cool. Because they don't use KZG or trusted setups, the decider, so the final step after you've done a lot of folding, still depends on the table size. But that's probably unavoidable unless you do something like lasso. Yeah, and so you can modify the check to be perfectly complete because there is this sort of subtlety in the B's. If you got unlucky and picked a beta that was equal to negative xj, then your prover would fail. Again, when working over a big field, this is extremely unlikely, but you can change the check slightly in order to avoid that. And then I guess most recently was this log GKR paper from Habak and Papini that was also mentioned in the last talk, where you can avoid committing to the A's and the B's entirely. So that's actually quite a big cost of log derivative lookups. And that's also part of the reason why MV-lookup's optimization is interesting. Because if you reduce the number of A's and B's that you're committing to, you reduce the prover cost quite a bit. So yeah, this is sort of the high-level outline, and then now we'll talk maybe a little bit about CQ specifically. So CQ stands for cache quotients. Yeah, name. Yeah, so just some preliminaries. In the previous version, I wrote everything using vectors and checking equations on vectors and so on. And now we're going to rewrite things using polynomials. This is, kind of boilerplate, but it's important because for CQ, we're going to use KZG commitments, and it has to sort of work with polynomials. So instead of sending x, m, and t, we'll send these polynomials that interpolate those values. Omega is just a root of unity. It's not really important that it's a root of unity. You just have to have Lagranges, and FFTs are efficient in this case. So the verifier will once again choose beta, and the prover will send the A and B, which are the reciprocals that we talked about before, but this time polynomials interpolating the reciprocals. In addition, the prover will send these quotients or commitments to these quotients. So this is kind of equivalent to the zero check. Here, it's just left unspecified how one actually checks that beta plus ti times ai equals 1. I think that's right. Maybe it should be mi. Anyway, here, this is how one might actually do that. You can convert it into polynomials and check that the equation in the numerator, the a times tx minus beta minus mx, vanishes everywhere on the roots of unity. So this is common Stark stuff, but maybe worth explaining. So now at the end, we're going to check these equations. We check that the sum of the values of A equals the sum of the values of B, which has this really nice form due to Aurora, as well as these degree 2 relations in the polynomials. So if you think about the left-hand side and you evaluate it at an omega to the I, you'll get exactly one of those 0 equations. So if it holds at all of the omegas to the I, then it's a 0 mod z, and so this equation will hold. So now what if the table is really big and we know it ahead of time? And we're looking up a small number of values relative to the size of the table. When we construct A, it'll be pointwise, it sort of lines up with the table. And we only have a non-zero value of a when we're looking up that value in the table. So we can say that a is sort of sparse in the Lagrange basis, because the Lagrange basis is sort of how you represent pointwise polynomials. So most of the values of a will be 0, except for a very small number of them. So it's m sparse. And we can commit to m sparse polynomials very easily. It's just m scalar multiplications. But q is not m sparse in the Lagrange basis. It has this weird form that depends on a and t and m and z and so on. So if we could find a basis where q is m sparse, then we could commit to q efficiently as well. And it turns out that such a basis exists. And it is almost exactly the same thing as the output of the FK algorithm. So this technique is used in calc as well as all of the other large table lookups, where you can compute a large number of KZG openings in t log t time. So if you were to compute one KCG opening, it would take t time, and we want t of them. So the naive algorithm would be t squared. You'd compute t of them t times, or yeah, t of them in t time. But you can take advantage of the structure of the problem and essentially perform an FFT on group elements to compute all of these openings, all of these expressions on the right-hand side, except for the omega to the I divided by n in t log t time. And you can multiply by the normalization in t time. So this only works with KZG. It's not even really clear what it would mean for other polynomial commitment schemes. And maybe more importantly, these checks down here, we're going to have to perform using a pairing, because we can't like evaluate the table polynomial, for example, because it's too big. So, given these pre-computed QIs that depend only on the table and not the values that are being looked up, we can commit to Q, which happily is actually the same linear combination as A, in O of M time, O of M scalar multiplications, or an M-sized MSM. Can also commit to A and M in O of M time in the Lagrange basis, because they just pointwise evaluate to the reciprocals and the multiplicities. And now we have these polynomials. We've committed to all of them except for t, which we sort of pre-computed in O of M time. And remember, z is just x to the n minus 1. So that's not something you pre-computed, I suppose. And so this equation is degree 2. This ax times tx minus beta, and so on. So you can evaluate it using pairings in the exponent. Yeah, so that's basically the core trick of CQ. So compared to the other big table lookup protocols, they sort of pull the values out of the big table into more like a little table, and they can reconstruct a quotient in n log squared n time, because you don't know where in the table the values you're looking up will be. So you have to use sort of general polynomial interpolation. Here, we don't do that. We just sort of get them, we like mask them out of the table and then sum them all up. And it turns out that actually, because the sum check that we want to do is just evaluation at 0, we can pre-compute KCG openings at 0. We can also pre-compute degree checks. And so all of that can be done in O of M time. So you'll notice that everything so far has actually been in O of M time, not O of M log M time. The only thing from CQ that takes O of M log M time is computing the quotient QB. That's for the kind of lookup side, as opposed to the table side where everything is done in O of M time. And this is just because we're needing to check this degree 2, the last line relation, bx, fx minus beta. And fx and bx are both unknown ahead of time, unlike in the second to last equation. So we need to actually use FFTs to compute the quotient. But that's not really fundamental, right? In practice, if you were to use CQ, the complicated part is the table side, because you have to have all this pre-computation and everything else. The lookup side can be done with anything. It can be done with any snark. You just have to check the kind of, the reciprocals are well formed and that they sum up to the same as the table side. So it'd be very easy to replace the QB with a sum check based protocol, for example, and that would actually make all of CQ O of m time at the cost of making the size of the proof log m, whereas as written it's constant size. So yeah, that's CQ at a high level. There was a follow-up work so originally CQ did not include zero knowledge. There's a follow-up work that adds zero knowledge to CQ. But yeah. So now I'll talk a little bit about ProtoStar lookup. This one is a little harder to get into without sort of breaking down the abstractions of ProtoStar, so I'll maybe talk about it at a little bit higher of a level. So ProtoStar, as you heard before, is a folding scheme. It's a very general folding scheme. It allows you to check any polynomial is satisfied for a witness. Unlike, say, for example, R1CS, where you have to encode your statement into a sort of rigid structure, matrices that are Hadamarded, or even CCS, which is kind of like R1CS with high-degree gates or Plonkish or all of these things. ProtoStar is just super general. Like you have a polynomial, you want to show it evaluates to 0. So, what we would want if we were going to do a log lookup in ProtoStar is just a polynomial that evaluates to 0. ProtoStar also supports these multi-round protocols, which is critically important for lookups because, as you'll recall, we pick a beta in order to evaluate and test the rational identity. And so folding schemes are composed of 3 protocols. There's the prover, the verifier, and the decider. The prover runs every time you want to fold an instance. The verifier checks that you folded the instance correctly, and the decider runs only at the very end and sort of checks that everything prior to it was done or was valid. And the point of this is that the folding verifier is very cheap. It's like O of 1 or O of log n, but like relatively low constant log n computation. Whereas the decider is like a full snark, like you have to check potentially lots of stuff in a very expensive way. So deferring all of the hard work to the decider, you don't have to do it recursively. So for a lookup argument for a folding scheme, what you would want, ideally, is to have the prover depend only on the sparsity of your lookup, right? So if you're doing m lookups in one folding, you want your prover work to depend on m, not the size of the table. This is a little bit of a weaker notion than CQ, where we want the prover work to sort of unconditionally depend on the table size. We're willing to give up that in favor of doing table-dependent work in the decider, not in the prover. So we do O of m work in the prover, O of n work in the decider. And the advantage of this is that it doesn't require KZG or FK at least. I suppose there's still maybe a little pre-computation, but yeah. So in ProtoStar, we can check any system of polynomial equations, and the log lookup is just a system of polynomial equations. We can see it in the very beginning here, right? We have to check that the sums are equal. We have to check that this 0 check is satisfied. So more or less, you actually just check that. Like it's a polynomial equation and you check it. There's important details in showing that it actually depends only on the sparsity of A. But I think at a high level, that's probably sufficient to sort of understand what we're trying to do. And getting into the how of it would require breaking into ProtoStar. And I also don't have slides describing that. So yeah, I think that's it. Yeah, no, thanks.
Thank you so much for visiting this knowledges. Yeah, questions?
I actually have two questions. So first, can you um, I wonder maybe you can use CQ for the decider part for ProtoStar lookup. Is it correct?
Yeah. Are the slides still there or no? I guess it doesn't matter. Yeah, you can totally use CQ for the ProtoStar decider. The trouble is that you so one of the big issues with folding is that you have to keep around this very large witness, and this is still the case for ProtoStar. You have to keep around a witness that's like the size of the table. So if the total number of lookups that you did during the entire course of folding was small compared to the size of the table, you could use CQ to verify or in the decider. If the number of lookups you did over the entire course of the folding was like roughly the same as you could still use it, but I'm not sure it would really make sense compared to say log derivative lookup or something.
Yeah, and I also looked a bit into MV. You can potentially use a higher degree gate for ProtoStar lookup, but I'm not sure if it combines with. Okay, whatever. I will ask you after.
Yep. And other questions? Okay, I think so far so good. So thank you so much, Liam, for all of this. Thank you so much. Yeah.